Hey everybody, my name is Sean Dwyer, and today I'm gonna be doing my presentation, basically on how linear algebra connects to physics, which is, I'll get into it, but a lot of ways, like so many ways. But yeah, I thought I would do this because I'm a physics major, so the entire time I was taking this class, um, I just saw the connections like every single time we learned pretty much anything. There was some kind of connection to physics. Obviously, being a math class, that makes sense, but specifically linear algebra. Linear algebra has a lot of physics principles kind of just intertwined throughout. So yeah, I'll be talking about that today. So to start, it's almost every single time there's a physics problem, just in any sense of the word, there's some kind of linear algebra involved. So, like we learned this year a lot about vectors. That was kind of like the basis of what makes linear algebra what it is. Um, and that's also kind of the basis of what makes physics what it is vectors. It's kind of like every single uh, anytime you encounter a physics problem, there's going to be a lot of vectors involved. And so, like for example, this GIF that I have right here of this the balls clicking back and forth. There's like so many vectors just in this one thing. So there's the tension vectors of the force of the strings holding up the ball. So those two um, on each ball, the two tension vectors going up and to the right or to the left. And then every time the balls are moving, they have a momentum vector, which I'll talk about more later, which is basically just their velocity times their mass moving. And also the whole time, constantly, they have a gravitational vector, which is just the force of the mass times the universal gravitational constant. Well, not universal, the one that we have here on Earth. Um, so yeah, it's just an example of just this one thing right here. Anything you could look at in the real world has just a bunch of vectors going on. Here's a few like specific things I thought of that where vectors are present in physics. Linear transformations. They're actually more, I'll talk about that in the next slide. It's like a reference frame transformation thing. So you would take like a vector and move it. I'll talk about that. Forces, free body diagrams, which is one of the most important things in physics, if not the most important thing. Torque, angular momentum, electromagnetic field theory, and yeah, like I earlier said, basically any physics-based problem has some kind of vector, which is linear algebra involved. This GIF is actually a wave, so it's not really a vector; it's light waves. But I just thought it looked cool, so I put it here. Um, right, so linear transformations. It's basically when you take either just an object that's stationary or an object that has some sort of velocity or acceleration, and you move it from one reference frame to the next. So, like I have this picture here. So this bottom left reference frame would be like S, and then this top right reference frame would be S prime. And you would take. So we learned about in linear algebra. Also, I learned about this in physics a long time ago. I, J, and K hat. So those are like the X, Y, and Z unit vectors. So like if this if there was like a point particle, let's say, on this plane to the left, which would just be S, the original reference frame, and it was moving with some velocity, let's say to the right, so it had a positive I hat direction to the right, then to transform it to the S prime reference frame, there's a formula. It's pretty easy. It usually has to do with if there's time involved between the two reference frames, or if they have the same time, um, then there's not really any time involved. But yeah, so it's pretty cool. I'm going to talk about these quantities more later, so I thought I would bring them up now. So x is usually denoted to refer to position, and so just like where something is in reference to the origin. And then v is usually in reference to the velocity of a particle, and p is usually the momentum of the particle, which is its mass multiplied by its velocity, which is a very, 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 very important physical concept. Um, so like I mentioned earlier, the free body diagrams, most likely the most important aspect of physics, at least for beginner level physics, when you're first learning how problems work and how to set up your problems. Um, so this is one that I actually drew. It's pretty simple. For this one, I was going for like if there's a mass on a spring and it was horizontal, and so like it's moving back and forth. So like the spring was like contracting and expanding over and over again. So I took this as like a snapshot when the spring is expanding and it's going to the right. So in the plus I hat direction. Um, so the force of the spring I have on the right of this mass is pointing to the right, and that's the spring pushing it. And then the drag force, which basically is just like air resistance. So if you're moving through air, the air is resisting that force, that movement. So that's to the left, but it's, as you can see, it's smaller because it's not enough to stop the particle from moving, right? So that's an important thing in free body diagrams is the size of the vectors. So like in linear algebra, we talked about a vector addition and subtraction. So here you would take the force of the spring and subtract the force of the drag from it, and as you can see, the net force would still be to the right. And basically, net force just means like the total resulting force from if you add up all your forces, or in this case, subtract some forces from others. Yeah, it's kind of it's kind of hard to explain some of this stuff really quickly, so I'm trying my best. But there's a lot of physics-based or linear algebra-based physics. Like it's just so much. So I thought I would just cover some of it. Here's another free body diagram. This is a free body diagram, but it's also more of an actual like 3D model that I drew. Like it's still, but the reason that it's a free body diagram, at least somewhat, is because it has the forces down and up on this space inside this cylindrical prism that I'm pretty sure this is I was doing a pressure problem. So if you have like a thing inside of like if you have a certain amount of area inside some kind of volume of liquid or air, then you have pressure acting on it from the top and the bottom and all sides, top, bottom, and left, right. So that's what I was drawing here. Here's another one. So as you see, we got all these vectors. For this is like a particle moving in some kind of uniform circular orbit. So at all times, you have the acceleration vector pointed straight in to the center, and as you can see, it's moving clockwise. So you have the velocity vector at these 4 different snapshots, moving tangential to the orbit at all times. So that's kind of a nice. You can see this would be a cross product if you took, because they're a 90-degree angle. I'll talk about cross products more. Yeah, like I just mentioned. So cross product, a pretty big thing we learned about this year in linear algebra. It's pretty big in physics also. It's used in a lot of different quantities. So yeah, as you guys learned, it's magnitude of A times. So the cross product of A and B would be the magnitude of A times the magnitude of B, and then the sine of the angle between them. So it's theta here. So yeah, I just listed 2. There's way too many to get into today, but I just listed 2. Torque and angular momentum, which are pretty closely related. So I chose those 2 because they both involve cross product and they're closely related. So we have a nice illustration here of torque. So basically, if you have some kind of object that has a certain amount of distance from the origin, in this case, it's being pushed with a force, and it has some kind of connection to that origin, like either like in this case, this ball, it has this rod connected to the origin, so obviously that constrains it in that way. But there could be a different example, like if you had like a planet in orbit also has torque because it's constrained by the gravitational pull of another planet. But yeah, so here you have the position vector, or actually, well, it's called position vector sometimes, but here it's specifically called the lever arm, which is the point from the origin to the object in question. So that's R. And then you cross product that with the force being applied. So if it's a force that's perfectly 90 degrees with the lever arm, then you're going to get maximum torque. So that's why that's calculated. So like if the force was applied at some angle that was like 150 degrees or something instead of 90 degrees in between, so I guess it'd be 30 degrees in between them. That would be a much less resulting torque, but it's the same force, but the torque is less, so it's going to result in less. Here we go, less angular momentum, which is the next thing I was going to talk about. So actually, on the last slide, I had a good illustration of angular momentum too. So the angular momentum is, well, okay. Essentially, the angular momentum is the cross product of the position vector and the momentum. So instead of doing the cross product of the position vector and the force, you do it with the momentum, and that results in a angular momentum, which either points out of the screen, or if you're looking at it like this, it either points out of the screen or points into the screen, depending on which direction your momentum is. So if your momentum is, like in this example right here, the momentum is up to the left, then it's going to point out of the screen towards you. So yeah, just a nice example of cross product. Oh yeah, so I thought also I would show you guys this. So in this physics class I'm taking right now, we've been doing it's called VPython, and it's like this physics-based 3D modeling software, basically. And I don't know exactly which one I want to run, but there's some good ones that have some like vectors. Oh, this one's pretty good. Right, so you can see it was like this was a planet, and these were 5 like space stations or like rocket ships or something. And you can see I have these arrows that I drew on the program, which are illustrating the force of each of the things, like the gravitational force of this planet on these space stations and the space stations on the planet. So as you can see, they're equal. This one's equal to this one. This one's equal to this one. I don't know if you guys can see my mouse, but um. So yeah, I thought that would just be cool to show you guys because it's another connection to physics. Um, and it's like you can see it in real time, which is cool. All right, so the last thing that I was going to get into, I actually didn't think that there were really much matrix involvement in physics. I knew about like the cross product. If you like set that up, then it's basically matrix addition and subtraction with some multiplication of scalars in there. So if you're trying to find a cross product, this is one way you can do it. I usually don't do it this way. I usually just find the magnitudes, and if I can find the angle, do it that way. It's in physics you don't. It's rare to. I don't really do it like this way, but I've seen people do it like this a lot. So yeah. Anyway, but so that led me to doing some research, and I actually found that there's a huge subset of physics. I'm probably going to get into later on. It's really advanced physics, but basically quantum mechanics, which I've talked about, but in the form of matrix mechanics, which is what they call it. So I'll give you guys some background. There's this guy Heisenberg. Don't know his first name, but he's talked about a lot in physics because of his uncertainty principle, which basically states that you can't know the exact position and momentum of a particle at the same time given initial conditions with a certain amount of certainty. Like you can know them both, but the more you know one, the less you know the other, basically. So if you know the position of a particle really well and you're like almost 100% positive of it, then you're not going to be very sure about the momentum. And that's demonstrated by this formula right here. So to insert d of x in P,